Okay, thank you very much, and thanks for the invitation to present here. So I'm Alex Normandeau. I'm a researcher with the Geological Survey of Canada here in Halifax, Nova Scotia. And today I'd just like to present some of the new research we've done over the last few years on the influence of cryospheric processes on marine geohazards. Apologies, I'm trying to switch slides here. Okay, so submarine landslides. I'll mostly focus on submarine landslide, but you'll see that there's some applications to other types of geological hazards. So submarine landslides are often orders of magnitude larger than their terrestrial counterpart, and as such, they represent major geological hazards. Now, the image here in the background is not to scale, but it's just to show what a submarine landslide looks underwater. And so these landslides can be a threat to coastal communities because they trigger tsunamis and also offshore infrastructure. So the triggers of submarine landslides are often identified through the use of cable breaks, repeat bathymetric surveys, and acoustic Doppler current profilers. However, that's mostly done in non-glaciated settings, so further down south, because it's very hard to monitor sedimentary processes on the seabed in glaciated margins in the Arctic or Antarctic, just because of resources and how far it is. So in these glaciated settings, many interpretations of the triggers of marine geohazards rely mostly on sedimentological analysis of their deposits. But we know that that's not very reliable from studies further down south. And so in glaciated settings, we also know climate change is leading to abrupt changes in cryospheric processes. So there's melting glaciers that's bringing a lot of sediments to the coastline. There's a reduction in sea ice as well, thawing permafrost that has consequences both on the coastal environment, but also in the marine environment, and also a rise in sea level. And these changes are really modifying the coastline in drastic ways. But how does that affect the marine environment? We kind of know a bit about how it affects the marine environment where we have seafloor mapping, and that's where we're lacking a lot of data. So regional seafloor mapping is really a critical first step to identifying the distribution of marine geohazards to see if there are submarine landslides or turbidity current channels in areas. But it does not really allow us to understand what causes them, because the problem is what we map on the seafloor happened in the past. We're not observing a new phenomenon in action. So that's where there's been a lot of efforts in the last decades to try to monitor and use repeat seafloor mapping to link marine geohazards to modern changes, in this case, in the cryosphere. And so just like on land, we were lucky enough with the advent of satellites that we were able to monitor changes in the cryosphere, but also on sedimentary processes on land. We don't really have that yet for the marine environment at the global scale, but we are trying as a community to map some regions, some selected regions, to try to understand what's happening on the seafloor in light of these changes in catchment scales or in the cryosphere. And so this leads me to just a case study of a fjord here in Baffin Island, and then I'll try to extrapolate those results to continental margin. And we can then discuss from there. So the case study that I'm going to present here is from Southwind Fjord in Baffin Island. So that's the red dot we can see here. And the reason we went there is that there was regional mapping that was done before in that area in 2013. And that's the multi-beam bathymetric map that we can see from that fjord. And what was really interesting is that you can see that there's a channel coming down from the fjord head deltas here. So we pretty sure that there are turbidity currents that are occurring probably every summer. And there was also a large number of submarine landslides that we can see here on the sides, and we can see it in the zoomed in image here. And so we thought if we want to understand what causes submarine landslides in Arctic regions or glaciated regions, then that fjord becomes really important because it seems to be pretty active. And so we were lucky enough that we started a short monitoring program over a few years. We deployed ADCPs. We had some issues with them, but mostly we did repeat seafloor mapping. And we were lucky enough that we actually saw something happening on the repeat seafloor mapping. So this here is on the right side is from that square here. And we can see the data, the multibeam data in 2013, and we can see that the seafloor is relatively smooth here. And then when we remapped it in 2019, we can see the change there on the seafloor where there's a new submarine landslide that happened. Now it's a small scale landslide, but it was still a good example to try to understand, okay, what happened between those years. So I'll just go back again, 2013 and then 2019. And then if we do the difference in elevation between these two surveys, we can see in the white spots the erosion caused by the landslide and the deposition at the base of the landslide. Now, we also had data in 2018. Unfortunately, the data was not as good as the 2019 and 2013 data. It was with a lower resolution multibeam echo sounder, but it still allowed us to see that there was a deposition of 3 meters between 2018 and 2019. So we were able to see that that landslide happened sometime between our survey in 2018 and in 2019. So that offered really a unique opportunity to understand what causes submarine landslides in glaciated settings. Now, the first thing that we saw also on the new data after the landslide happened are these iceberg pits at the head of the headscarps of the submarine landslide. So you can see here the slide scarp, you have the headscarp here from a side view, and you can see those iceberg pits here and here. So we thought immediately, well, would it be possible that these iceberg pits caused the landslide? So again, we went back to the bathymetric surveys before from 2013, and we could see that there were no iceberg pits in that circle there that we see. And then in 2019, these new iceberg pits that are there, and so we thought, well, most likely those probably triggered the landslide. So then, of course, we want to prove that even more. So we went to satellite imagery, and that's where, again, if we have repeat satellite imagery, you can start understanding the processes. And so we could see icebergs coming in and out in the fjord in August 2018. And then in August 27th, we can see an iceberg coming and then grounding early September at the exact location where the landslide happened. And so we'll just focus a bit more on that, but just as an anecdotal before, is that actually on August 27, 2018, when we can see that iceberg coming in the fjord here, if we zoom into this location here, we can see that that is actually us on a research cruise in 2018 collecting the data for this study. And so that's the Canadian Coast Guard vessel Hudson. And so we have also some drone footage where we can see our vessel here and us doing some surveys, and then the iceberg in question just at the back here. So we actually had some measurements of that iceberg coming in the fjord at that time. So incredibly lucky coincidence here. And so if we zoom in on what happened in early September 2018, this is what we have. So here is the hillshade image of what is assumed to be the seafloor on September 4th, and then some transparency. So the white dot here is the iceberg that we just saw on the satellite imagery. And so on September 4th, the seafloor is assumed to be stable, or there's no landslides. And so icebergs are coming in and out and then grounding in that location. And then on September 9th, something happened, and I'll just go back again, and you can see that the iceberg actually switched position. So it seems like the iceberg actually flipped, so capsized, and then impacted the seabed exactly here at the location of the landslide, and also split in two. So you can see another iceberg here. So that split from the original iceberg that impacted the seabed and caused the landslide. And so this is then that iceberg stayed there for a month or so afterwards. And so we have quite good evidence that icebergs here triggered a submarine landslide in this fjord. Now, can we extrapolate those results to continental margins? Can we see some evidence of iceberg triggered landslides on continental slopes? And so we started looking at what is the modern distribution of icebergs originating from Greenland and from Antarctica. And the yellow line there that you see is the shelf break, essentially at 500 meters water depth. And that's also the maximum depth of modern icebergs in Antarctica and Greenland that have been measured in the past. And so wherever that line, that yellow line intersects the red zone is where there's potentially iceberg triggered submarine landslides. And so of course, we're missing a lot of multibeam bathymetric data in those locations, but where we do have some data, as for example, here on the Scotian shelf, so just offshore Nova Scotia, we can see series of bottleneck submarine landslide coming down the continental slope. And that's starting in approximately 200 meters water depth and extended to 1,000 a meter water depth, and those extend for kilometers downslope also. And what's fascinating here is that they originate from single individual iceberg pits, as you can see here at all these numbers that we see along the margin. And so if we focus here on 8 here, and we'll just look at that example, we can see that there's an iceberg pit here in the multi-beam image, and then a bottleneck kind of landslide going down for multiple kilometers. And if we look at profiles across this, we can see here on the right that the iceberg pit has a depth of about 8 meters, and the failure plane depth of that landslide is about 10 meters. And so it seems like the iceberg probably capsized, or maybe it's a nice sheet whenever that happened, where there was a collapse of a big iceberg and then hit the seafloor and generated those landslides across that margin. Now, interestingly, also, we see a lot of iceberg pits at canyon heads in that region and along in a lot of regions where there has been glaciations in submarine canyons. So we're also thinking, well, is it possible that icebergs that hit the canyon heads create submarine landslides or turbidity currents that then flow down submarine canyons? That's an open question. We don't have an answer for that, but the relationship here is quite interesting. And then just another example here, that's from a study from Steen and Al 2016, and that's on Lomonosov Ridge, where we can see those lineations. Those are glacial lineations, and we have those submarine landslides on the scarp there. So is it possible that there's a relationship between the glacial lineations there and the slide scar? The question is still open. And so I'll just finish on this image here and a couple questions. This is an iceberg that we can see here on the left side. That's A68 coming from Antarctica, from the Larsen Sea ice shelf that broke in July 2017, and then it navigated along the iceberg alley there in Antarctica. And there was a lot of talks in February because it was going to hit South Georgia Island that you can see here. So there was a lot of talk about the ecological consequences of that. But what would have been the marine geological consequences of these giant icebergs breaking from Antarctica and hitting the continental margin or the slope around South Georgia Island? And has that happened in the past, and has that created a landslide in the past or not? And so I think there's a lot of studies on modern slope processes in Antarctica that could look at these types of processes. And then the other question is what other triggers of submarine landslides are we missing due to lack of repeat mapping and monitoring data? We were just lucky enough to be at the right place at the right moment for finding that iceberg can actually trigger submarine landslides, and that wasn't really known beforehand, or at least was never observed. And so what other processes are we potentially missing just because we're not looking or doing this repeat mapping that we can do online with satellite imagery? So I think there's a lot of work that needs to be done towards the monitoring and the repeat mapping to try to observe these processes rather than interpret them from sediment cores. So on that note, I'll just like to thank quite a lot of people that are always involved in these research crews. As everybody knows here, those are quite collaborative crews that requires a lot of people on deck helping out. So thank you, everyone.